So hello again. We're going to be talking today about and OR gates. It's something that we've covered before and we've used before, but now that we know truth tables, we'll be able to visualize it better. And we are also going to learn how to create basically any circuit with only and OR gates, which is something that we can do because if we remember to last video, both sum of products and product of sums can use only ands and ors. So yeah, it's something that we definitely need to pay attention to. I have these diagrams already ready, the AND gate, and this is the truth table. It's very intuitive to imagine it. It's just going to be on when all of its inputs, the number of inputs can be as many as you need them to be, are 1. So all of them need to be on when in order to have a 1 output. So that's something definitely to keep in mind. The more inputs you have, the least likely it'll be a 1. For our OR gate, we're gonna have we can have as many inputs as we want. Of course, there are physical limitations when implementing these circuits, but theoretically we can put in as many inputs as we wanted to. It will be on when either A or B is on, so also very intuitive. The only thing to remember is that for the OR gate, when both A and B are on, it also counts. So you're going to have a 1 just like the AND, but you will have these 2 additional ones. So that's a good overview. Now let's look at how we can actually implement a circuit, any circuit we want, with these 2 gates. So I have attached this truth table that I think is a good exercise to do. You might notice that there are only a few ones. This is important because at this point we don't know how to simplify circuits yet using K-maps, which is the easiest way to do it. We only have Boolean algebra, which would take a very long time for a function that includes 3 variables. That's why there are a few ones, and I'm going to show you what is the best way for me that I like to draw it, and maybe you can use that or you can use something different. The important part is that you get all the inputs and outputs correctly. Let's do the same thing that we were doing for last video, and let's try to find the function f that goes along with this output. So like I mentioned last video, you're going to want to choose between sum of products and products of sums. You have to be familiar with both, but I, for example, prefer sum of products. It is the most commonly used, and overall I find it easier and to use. So let's do this for the output. So again, we're going to pay attention to the ones. So I've marked where the ones are at the beginning. This is something really useful that I do because otherwise it's easy to get lost between all the ones and zeros. So let's look at this first one, and we're gonna again consider the zeros as A naughts and the ones as A's. So let's start with our first term. We're gonna have A naught, B, C naught. Then our second term will be A, B naught, C naught. Our third term will be A, B, C. And finally, our last term will be A, B, and C naught. So these terms are ands. So whenever we write a variable that is multiplying another, sort of multiplying another, remember that that is an and connection. So that's to keep in mind when we're going to draw the circuit. So for now, we're just going to write the function f as the sum of these products. So here's the function completed. So just like I was saying before, the multiplications will become AND connections, and the summations will become OR connections. So let's see how to do that with actually drawing the circuit. So I brought the function to the top here so that we can start creating the circuit. This is the process that I like to do. I find it the easiest. So the first thing I like to do is draw my OR gate that will connect all of the ANDs. I usually draw it pretty big because it will connect numerous inputs. You will always have as many inputs into the OR gate as you have terms. So in this case, we'll have 4 inputs. And then I'm going to draw however many terms I have, I'm going to draw that many AND gates. So here I will draw 4 AND gates. And then I will connect them to the OR gate. Okay, so most of your circuits, when you're doing sum of products, they will look like this. They will look like an OR gate with ANDs, and always remember that the number of ANDs and the number of inputs into the OR gate will always be the number of terms. So yeah, if you were doing product of sums, it would be a big AND connecting a bunch of ORs. So that's something to keep in mind as a parallelism, but again, I would choose one method and stick to it. Okay, so for this part, I'm gonna move this table a little bit so that I have a little bit more room. Okay, so now that I have more room, I'm going to do what I like to do just to not get confused or have the circuit be very messy. It usually happens when I try to make it, you want all of the same variables to come out from the same origin. So what I like to do is I like to say A, B, C, and these are our variables. So I drew a line for each of these variables, and these will be the sources for all of our combinations. I also like to add the NOT component, so to do that I will just draw a NOT gate, which we covered in a past video, and a line that shows a NOT. Okay, so I drew both the variable and the NOT component of the variable for all of the variables present in this function. So now what I'm going to do, let me just lower this so that it's better lined up. So that is something to be careful of. You're going to end up making connections that are kind of horizontal, so you do want to make sure that they're lined up properly, which is something that I should have done earlier. So now that we have these variables, we're going to connect them to the ANDs. So we're going to connect the variables to each of their terms. So let's start with our first term, the A naught, B, C naught. What I like to do to distinguish a connection from a just crossing a line is to do a dot where I'm connecting that cable to. So for example, for A naught, that is going to be our first variable inside this term that we're going to connect. I'm going to do a little dot here to show that this input will be from A naught. And I'm going to cross all the variables and get to the AND gate. And then I'm going to do the same for B onto the same gate. And then finally for C naught. So that's our first term. That's seemed pretty easy, right? I recommend this way of doing it because number one, you'll always know where to pick from, and the cables won't become as intertwined as they would in some other circuits. So this one's pretty simple. It might be easy to do just, putting A and then just connecting A to everything, and then B and connecting B to everything. But when you get to more complicated circuits, you don't want to be doing that. So that's why I use this method, and I really recommend it. It's really easy. So now we're going to do A, B naught, C, and then again it'll be very easy. We're going to connect A, so we do a little dot in A, and we connect it to the second gate. We're going to do a dot in B naught, connect it to the gate, and finally C naught, and connect it to the gate. So I'm sure you're already understanding this, so I'm going to go ahead and do the last two terms, and you can compare your answers. So this is going to be our answer for this problem. It's going to be the circuit that will behave as the desired output that is represented in this table. As you can see, let me number the terms so that we know which one is which one. So this is 1, 2, 3, 4. It's going to be 1, 2, 3, 4. Okay, so yeah, I hope this is pretty easy to understand. I do want to make sure that also the order does not matter. We went over that in Boolean algebra basics. So yeah, so you can, the first logic gate can be the fourth term. It doesn't matter. And, that's basically it for the ands and ors. You can see how we can create any desired output with this kind of circuit. Later on, we'll be able to simplify circuits so that it's much easier to create more complex circuits than the ones that we are covering now.